Okay, now I have an electrical system that's very similar to that second order pendulum system that I talked about. In this case, what I have is a series RLC circuit. And the two forms of energy storage in this case are not potential and kinetic, but basically the capacitor voltage energy and the inductor current energy. Okay, so in this particular case, I have a 1 microhenry inductor and a 10 to the minus 4 farad capacitor. And I represent the loss in the system through this resistor. Now in this particular case, I'm going to start out initially by putting some energy into the capacitor. So t equal to 0, the capacitor voltage is 10 volts, and the inductor current is 0 amps. All right, so that's kind of the equivalent of taking the ball and pulling it up, away, kind of higher a little bit to that 20-degree angle. So in other words, giving that ball some potential energy. In this case, what I've done is somehow I've put some energy into this capacitor, and I'm going to discharge it. Okay, and I'm going to start out initially with basically 0 resistance, so no loss in the system. So with a 10 to minus 4 farad capacitor, the initial energy in the system is 1/2 CV squared. So at 10 volts, that becomes 5 millijoules. So let's run that simulation here. All right, so I'm going to run that. I run them. Okay, what I can see here on the top, this is the inductor current here in the yellow, and the bottom is the capacitor voltage. So let me zoom in onto the first period or so. So I see the capacitor voltage starts at 10 volts, just like I said it would. I see the inductor current starts at 0, just like we said it would. And then what I have here is sort of a cursor that I can move along the two waveforms. So one thing I want to notice is the capacitor voltage starts at 10 volts and eventually goes to 0 volts. Right? At that point, there's no energy here on the capacitor. But I see that there is about 100 amps. In other words, I see the inductor current is peaking at 100 amps. If I look at that and I take that 100 amps and I look at this 1/2 Li squared, well, with a 1 microhenry inductor, that's 5 millijoules. So what's happened is the 5 millijoules of energy that was initially stored in the capacitor is now 5 millijoules of energy stored in the inductor. And this process is going to continue forever. Basically, an exchange of energy in the capacitor is being exchanged with energy in the inductor as time advances. And that's going to continue forever because there's no loss in this system. This is equivalent to the situation where I had no loss in that pendulum system. And I had initially a t equal to 0. So back here, I had all potential energy and no kinetic energy. And then eventually I have all kinetic energy and no potential energy. The same thing is happening here. Now, let's say instead that what I do is I put a little bit of loss in this system. So let's put in 0.01 ohms. Okay? And I'm going to keep that 10 volts initially. And I'm going to run this simulation. And now I see my result. What I see is that slowly over time, the amplitude of this oscillation decays. And the reason it's decaying now is because the energy in the system, every period of this oscillation, the energy in the system is being lost. A little bit of it is lost in this resistance. Okay, so if I zoom in again over the first couple of periods, what I see again is that initially I have about 10 volts here on the capacitor, 0 amps on the inductor, and then at some point the capacitor voltage goes to 0, right? And the inductor current is kind of maxing, but notice it's a little bit less than 100 amps, okay? And then over time, there's a little bit less voltage on the capacitor every time, and a little bit less current on the inductor every time, because some of the initial energy that we had, that 5 millijoules of energy, is being lost in the resistor. Now if I keep increasing this guy, let's say that I take it now to 0.1 ohms, and I run it again, now the energy should dissipate even faster. Okay, and I see that here. So let's zoom in a little bit some more, right? And I notice that again, I start at 10 volts. In other words, I start at that 5 millijoules, start at 0 amps, all right? And slowly over time, in this case, I get to 0 and I don't have as many oscillations because there's a lot more loss as I go through any one period now. So if I increase that loss even higher, so let's take that resistance up. Let's go to 1 ohm, okay? Now I have a lot more loss in the system and I run this simulation. Now, if I look at this guy, let's zoom in a little bit. In fact, let me do this, okay? Now I can see what happens. I start at 10 volts. I still start at 0 amps. Maybe that's a little hard to see. Let me zoom in, okay? So I start out at 10 volts, still start out at 0 amps. And very quickly that inductor current peaks. But then both the inductor current and the capacitor voltage go to 0. So let's bring everything back in. So I see that capacitor voltage just drops to 0. Now this, if I look at that capacitor voltage, it looks sort of like a first order system. Now that my loss is so high, I've lost that kind of oscillatory nature. So if there's no loss in the system, what I have is this exchange of energy where I start with electric energy in the capacitor and go to magnetic energy in the inductor, and it just sloshes back and forth forever. As that loss begins to increase, what happens is I still have the exchange of energy between the capacitor and the inductor that just kind of continues for a while, but every period I lose a little bit more energy, and so the size of that oscillation gets smaller and smaller. That's my underdamped scenario. Eventually, as that loss gets higher and higher and higher, I lose that oscillatory nature as the energy in the capacitor is mostly just lost and isn't really exchanged as much with the inductor. And that's when I get to this kind of behavior, which is overdamped, which really looks a lot more like a first order system. And if I increase this guy even further, let's say I tried 10 ohms, I'll just overdamp it even more. And there we go. Now I see it looks like this guy just sort of decreases towards 0. Now notice he's slowing down in his decrease. All right. But essentially he's still got this overdamped behavior. In other words, he never overshoots. He never has this sort of oscillatory behavior.